magnetic potential. So we have discussed the electric potential very extensively, right? It is a very important parameter. We use it in other subjects as well. In networks and power systems, potential is a very important parameter, right? So now we are going to discuss the magnetic potential. So in the magnetic potential, whether we consider it to be a scalar or a vector, that is one important point. Okay, so what is electric potential? It is a scalar quantity. Okay, here there is going to be scalar as well as vector potential. So why that is the case, you will understand. Okay, once we discuss, you will understand. So let Vm be the scalar magnetic potential. So this we are taking analogous to the electric potential V. So since we are taking in an analogous way, okay, so we should think about the relationship between the electric field and the potential. What was the relation? E bar is equal to minus del V. Okay, so in a similar manner, we are going to write a equation in the magnetic field. Okay, so what is the analogous quantity to electric field in magnetic field? It is the magnetic field intensity H bar. Okay, so this is equal to minus del Vm, the gradient of Vm. But we know that del cross H, what is del cross H? It is equal to the current density J bar. Right, now instead of H bar, substitute this expression minus del Vm. So what you are going to get? Del cross minus del Vm is equal to J bar. So if you remember differential calculus, if you take a scalar function, say f, this is a scalar function. What does it mean? Scalar function is something which does not have the direction. Okay, so del cross del of this scalar function, first you take the gradient of it and then you apply, when you do gradient on a scalar function, you are going to get a vector function. Okay, so curl of that vector function, if you do, you are going to get 0. Okay, so this is one important identity in differential calculus. Okay, so here also, if you can see, here you have del cross minus del Vm, right? What is Vm? It is a scalar function, scalar magnetic potential, right? So scalar function is here, you are finding the divergence for gradient first and then you are finding the curl of that vector. So what you should get? You should get this expression is 0. Okay, so you are going to get the current density J bar is equal to 0. Okay, so what does this mean? It is not always true. J bar is not always 0. So what it means is that only for the cases wherein the current density is 0, the scalar magnetic potential can be defined. Okay, if current density is not equal to 0, then scalar magnetic potential cannot be defined. In that case, we have to take up the vector magnetic potential. Okay, so you can write it down here. Therefore, Vm can be defined only in a region. So this is just something that you have to remember from differential calculus. So therefore, Vm can be defined only in a region where the current density J bar is equal to 0. Okay, so we define a, so we have a vector magnetic potential as well. So now the question is, how do we define the vector magnetic potential? So vector magnetic potential A bar is defined as B bar is equal to del cross A bar. Okay, curl of vector magnetic potential is the magnetic flux density. Okay, so you can say Vm is the scalar magnetic potential, and this relation with respect to the magnetic field intensity is minus del Vm. and A bar is the vector magnetic potential. So this is related to the magnetic flux density as del cross A bar. Now for a line current, that is a current carrying conductor, as simple as that. Okay, you can write down the vector magnetic potential as integral line integral, this is the line integral, mu naught I dl bar by 4 pi r. So this expression, this is taken analogous to the electrostatic fields. Okay, you don't have to know the how it is derived, just remember this expression. Okay, so for surface current, A bar is equal to, so here there is a surface current, right? There is a surface and we have a ampere per meter, what is the current, right? So that is the surface current. So this is equal to surface integral mu naught K bar ds divided by 4 pi r. Okay, surface current will have direction, unlike the current doesn't have direction. So we are taking the displacement vector, but K bar, it has direction. Okay, and finally for a volume current, so this is nothing but in terms of the current density. Okay, so A bar is equal to the volume integral mu naught J bar dV by 4 pi r. Okay, so this is how the vector magnetic potential is defined for various currents, line current, surface current and volume current.